Hello, my name is Rafael Lopez, and this is my mathematical visualization video. In this video, we're going to cover the Schrodinger equation in order to explain how the quantum tunneling effect works. We're first going to go over the equation, then we're going to go over an illustration of how the quantum tunneling effect would happen in real life, and then see its practical applications. The first things first though, in quantum mechanics you need to know the outcome of a measurement can never be predicted. The best thing we can do though is predict the probability of getting a particular outcome. And in quantum mechanics law though, you should know we'll use the Greek letter phi though. The Greek letter phi is meant to represent the wave function of a particle though. And what that means though, a wave function is a kind of probability though. It's a kind of probability though. It takes on complex values. By taking the absolute value of the complex values though, we can find the probability of it though. Excuse me, my mistake. Technically in quantum mechanics though we use amplitudes. Classical objects have probabilities though. Again, amplitudes are like probabilities though, except they have complex numbers in it though. And that's going to be very important though in solving the problem though. Now the first things first though, we're going to keep things as simple as possible though. We're going to show a fairly simple, straightforward case of the Schrodinger equation. Now, to warn, I feel like I should let the audience know though, in order to understand the Schrodinger equation though, very well though, you need to have a very good understanding of differential calculus and integral calculus though, with a little bit of linear algebra though. I mean, you can still watch follow along. It just you might not be able to get some of the details though. Now, in the Schrodinger equation right here, well, what we put into the Schrodinger equation though is the probability function though, which I have in purple though, and that's put inside to the Hamiltonian operator though, which is the h though. Now, the thing you need to know about say the quantum tunneling effect though, it's a little bit strange though. Let's put it into classical terms though. Let's say there's a ball though, on one side, and there's like a wall on the other side. Now, mind you, I use the word wall somewhat figuratively. We don't really need a wall in the more traditional classical sense. It's more as a stand-in though, because the more technical thing for wall is just more. It's a potential wall, or it's some kind of energy barrier, some kind of threshold energy barrier though. Then in order for the particle ball to go all over the other side, it needs the energy of the ball needs to exceed above a certain energy threshold though, which is what the wall is though. And again, in a more mathematical sense though, this blue wall as you can see here would be considered a step function though. Here's a representation of a step function using Wolfram Mathematica. Now, step function is just a function where everything is zero though, except in a certain interval though, and that's what a step function is. So this is where it starts getting a little very strange though. When you observe the behavior of the ball though, excuse me, the peak of the probability distribution is moving at a constant velocity. It means the peak will stay the same, except when it moves though, the width of distribution becomes greater. It becomes wider though. Well, what does this mean though? Now we're going to need a different principle of quantum mechanics to understand that. We're going to need the Heisenberg uncertainty principle though. And again, for those of you who may not be aware though, the Heisenberg uncertainty principle states that any particle, let's say an electron, cannot have a precisely defined position and momentum at the same time. So what that means is that the behavior of the particle isn't really like a billiard ball though. It's like a wave function though. And when the position is known well though, that means the momentum cannot be known well though. And also that leads to have a very strange effect though, which means part of the wave function has a somewhat larger momentum than the average, and therefore a larger velocity, and that runs ahead. And by that same token though, some of the wave function has a somewhat lower momentum and a smaller velocity as a result, and that lags behind, which is called dispersion. And what happens though, as a result though, even if a ball doesn't have enough energy to go over the threshold, in the quantum realm, which is anything about the size of electrons though, there's actually like a certain non-zero probability that this ball will tunnel to the other side though. At this point, you're saying to me, Raphael, why do I need to know this though? So what? And that would be an excellent question though. Let's just say you want to work as an engineer at Sony though, or at a Blu-ray manufacturing company though. Well, the laser inside the Blu-ray player though, which is right here, is a quantum well device. There's a special crystal inside though that has holes smaller than the wavelength of an electron. The electron that falls into one of these holes gives up. When the electron falls into one of these holes, it becomes trapped functionally in a zero-dimensional space though. But once its position becomes fixed though, the momentum becomes indeterminate and it tunnels out of the hole though, making room for another electron though. But in the process of tunneling out though, excuse me, a photon of light is released though. So as strange as this behavior may be though, it can be exploited for a practical purpose though. You're a Blu-ray player though, or let's say you want a flash drive or external memory drive though that uses NAND flash memory though, which is employed in SSDs and USB thumb drives. Those use a certain device called a floating gate transistor though, which again though too, whenever you put any bit into one of these hard drives though, or write any data on it though, it causes an electron to tunnel onto the hole though. So again though, this might seem weird because it is very weird though. But again, these have a practical application though. And if you want to ever go to software engineering or hardware engineering for computers or Blu-ray players though, you're going to need to know it very well.